I am delighted to present our work, Gaussian Scenes, Post-Free Sparse-View Scene Reconstruction using Depth-Enhanced Diffusion Priors, accepted to TMLR 2025. This work was done in collaboration with Prakhar Kaushik and Professor Alan Yule at Johns Hopkins University. The goal of our work is reconstructing the 3D world we see around us from sparse unposed images. So given only a few views of a scene like 3, 6 or 9, we ask the question whether it's possible to reconstruct the entire scene from only these sparse observations. In traditional post-Sparse-View scene reconstruction, all images from the dense observation set are fed to an SFM pipeline like CallMap to estimate cameras for the entire scene. For cameras for which ground truth images are available are used as training cameras, while the remaining cameras are used as novel views. In such a setting, when rendering from novel views, one does not go beyond scene bounds like into the walls of a room or into the earth, as the novel views are accurately aligned with the training cameras. This, however, relaxes the sparse view constraint, as one is reliant on the dense observation set to accurately obtain novel views for the entire scene. In post-free sparse view scene reconstruction, one cannot access the dense observation set for obtaining novel views of a scene. Instead, novel views are sampled from elliptical, spiral or B-spline trajectories fitted to the training cameras. This of course makes the problem more challenging. For our work, we pick challenging 360 scenes from MIPNA 360 and DL3DB 10K datasets with minimal overlap across training images. In such a setting, a traditional SFM pipeline like CallMap does not work due to insufficient matching features across training views. Instead, we rely on a data-driven 3D foundational model called master to estimate initial geometry of the scene like camera parameters, depth maps, and an aligned 3D point cloud. Once we obtain the initial cameras and 3D point cloud from master, we initialize 3D Gaussians at all of those points and jointly optimize all the camera parameters and 3D Gaussian attributes to obtain an initial reconstruction of the scene. However, as one can observe, the reconstructed scene has several issues like missing details in large parts of the scene, as many parts of the scene are unobserved in the training images, as well as several Gaussian artifacts when rendered from novel views. To reliably capture empty regions and artifacts in a novel view render, we design a pixel-aligned confidence measure based on light transmittance and Gaussian density. The intuition behind this measure is a pixel will have high confidence if there is low cumulative transmittance at that pixel due to significant light interaction with 3D Gaussians, and also if there is consensus among a large number of Gaussian primitives while rendering color at that pixel. While rendering a 3D representation fitted to sparse views, we observe that our confidence measure accurately captures empty regions and Gaussian artifacts, while a similar measure proposed in the 3DJS enhancer paper leads to several false positives. This is because their measure incorrectly assumes that well-reconstructed regions are represented by several small-scale Gaussians. Such regions are represented by a few high-opacity large-scale Gaussians, which does not lead to a false positive in case of our measure. For our measure, the number of contributing Gaussians n contrib would be low, but the cumulative transmittance Ti will also be low due to the high opacity of the Gaussians. As such, these flat monotonous regions are still flagged as high confidence regions. We design a diffusion-based generative approach conditioned using our proposed confidence measure to synthesize plausible content. To train this diffusion model, we create a dataset using open-source multi-view datasets. For a given 360 scene and its sparse view subset, we first run master to obtain initial cameras and an aligned 3D point cloud. Rendering the 3D representation from a novel view produces RGB renders and depth maps with empty regions and artifacts. Our model comprises the stable diffusion 2 unit and its variational autoencoder, which are fine-tuned further for post-free novel view synthesis. We condition the stable diffusion unit with clip features of input images for semantic context, plucker embeddings of trained views, and sampled novel views for geometry information. We use trainable film modulation layers for conditioning different layers in the down and mid blocks of the unit using layer-specific scaling and shifting parameters. The artifact-ridden RGBD render and confidence map are concatenated to the input convolutional layer after being compressed into the latent space. The ground truth RGBD image is also similarly encoded, noised corresponding to a random time step, and concatenated to this convolutional layer. The unit predicts the noise in this noisy latent and is trained using the usual MSE loss. At inference time, the ground truth RGBD image is replaced by pure Gaussian noise, which is denoised over several time steps to obtain a clean RGBD image. With our fine-tuned diffusion model, we iteratively distill the 2D diffusion priors into the initial 3D representation obtained from master plus 3DGS. We add the synthesized novel views to the training stack every 500 iterations. Novel views are sampled from an elliptical trajectory fed to the sparse training views. Every iteration we pick either a training or novel view. The usual 3DGS loss is used for training views, while novel views have additional depth and perceptual losses. This process is repeated for around 10k iterations till we have a 3D consistent representation. Here we show a qualitative comparison of Gaussian scenes with our baseline master plus 3DGS. As one can observe, even for the extreme view setting of just 3 views, our method is able to generate plausible scene content while also restricting Gaussian artifacts in distant ambiguous novel views. And here is another example using a 9 view split over DL3DV10K test scene. Thank you for listening. For more details on our method, comparison with related works, code, datasets and models, please visit our project page.